Okay, here's another assortment of questions from our Oxford text, and the first one is number 2 from exercise set 8E, where we have two events, n and m, and we are told the probability of each of those two events. Probability of n is 1/5, and the probability of m is 1/10. And we are also told that the probability of the union must be 3/10. And we're being asked whether n and m are mutually exclusive or not. So if you have mutually exclusive events, the probability of the intersection of those events is actually 0. So in this case, probability, if we have mutually exclusive events, we'll say the probability of n and m must be 0, because the number of elements, I guess, in the set n and m would have to be the null set or the empty set. And another way of setting this up is just I guess, include your entire rule of sum or addition rule, where you could say, well, the probability of the union of two events would be the individual probabilities added together. And then to take some care to make sure that you're not counting the overlap twice. So the entire probability, the entire circle, I guess, an Venn diagram of n, and all the probabilities in the m circle. And of course, if there is an overlap there, you would have counted it twice. So you have to take some care to make sure you don't count it twice by subtracting it once. Now, of course, if we have mutually exclusive events, you would also just look at that and say, well, this is going to be 0 if and only if we have mutually exclusive events. So that means your rule of sum is a little bit simpler if you're dealing with mutually exclusive events. So let's assume that these are mutually exclusive events. We'll look at the individual sum of these two probabilities, which will be 1/5 plus 1/10. And if we can add those together and get the correct union, then we have mutually exclusive events. So 1/5 plus 1/10 is, of course, going to be 2/10, the common denominator, plus 1/10, which is 3/10, which is the correct probability of the union, because that was, of course, a third piece of, I guess, given information. And if that doesn't make sense, well, a picture is worth 1,000 words. Here is a Venn diagram of the situation, and I guess normally when we're working with mutually exclusive events, we don't even bother to overlap our circles. We kind of make the effort to keep them separate, and then we can see these two individual probabilities are completely separate from each other. Since there's no overlap, the probability of that overlap is 0. And I guess just to recap here, probability of n is 1/5. Of course, it's 0.2 in decimal form, and 1/10 is 0.1 in decimal form. And we can see that outside of those two events, the probability of neither event happening is 0.7, but that hasn't been asked for in this question. Just to give you the visual of what mutually exclusive events look like and why we're able to ignore the probability of the intersection. Okay, our next question is number 3 from exercise set 8F, where we have two boxes, and the first box contains 3 cards labeled 1, 2, and 3, and the second box contains 4 cards, the numbers 2, 3, 4, and 5, and we are choosing a card at random from each box. And letter A wants us to, I guess, list the sample space, or you can use a diagram to help you summarize the sample space, whatever diagram you prefer. I think a tree diagram would make a lot of sense here, or a table would work as well, similar to how you would set up a pair of dice and looking at the sums of a pair of dice. But before we do any of that, let's have a look at our 2 boxes here sketched in front of us. We got 3 cards in box number 1 and 4 cards in box number 2. It should be pretty obvious that we can use the fundamental counting principle to count our number of outcomes in our sample space. We have 3 choices we could have from the first box, and for any one of those choices, there's 4 remaining in the second box. So 3 times 4 would be the 12, which would be the number of outcomes in this sample space. Now, just to make sure how you, I guess, how the so you know how the fundamental counting principle works, you could hypothetically say we could have the number 1 as our first selection in box number 1, and then after that we would cycle through any of the 4 possibilities from the second box. So you could have a 1 followed by a 2, followed by a 3, 4, or a 5. And right now we got 4 possibilities listed. And I guess we'll circle that just to let you know that that's my, I guess, hypothetical first choice, and cycle through all the possibilities. And a second hypothetical would be to start with 2 in the first box, and then, yes, cycle through all 4 possibilities out of the second box. So we'd have 2 followed by another 2, by a 3, by a 4, and by a 5. And if you can list your whole sample space, it's always a good idea, and I guess it's an especially good idea because we're being actually asked to list the sample space, but it usually is a good thing to list if you're looking at just calculating probabilities. So our third hypothetical is starting with 3, and then of course cycling. I guess I got the wrong color, but it doesn't matter. Starting with a 3 and then cycling through the 4 possibilities out of box number 2. So 3 followed by a 2, by another 3, by a 4, and by a 5. So hopefully you can see how the fundamental counting principle is a shortcut to getting at least counting the number of outcomes in your sample space. And if it's only 12, I think regardless of whether you're asked to do it or not, you probably should list your sample space, because that will help you greatly when we get into letter B here and start calculating some probabilities. So there is letter A. We'll say letter A. And then we move on to letter B. We've got a ton of probabilities, I guess, to calculate here. So let's take them step at a time. So the first one is the cards have the same number. So, of course, 1 followed by any of these other cards, there's no duplication, but we can see there's a pair of 2s, and there's also a pair of 3s that are possible. So this probability is going to be the number of favorable outcomes 2 divided by the total number of outcomes in our sample space. And of course, you could say that's 1/6, but 2 out of 12 works as well. And I guess that's little Roman numeral 1. Okay, so on to little Roman numeral 2 in part B, where now we're being asked to determine the probability that the larger of the 2 numbers drawn is a 3. So I guess we'll cycle through our 12 outcomes and say, is the bigger number 3? And of course it isn't there, but it is with a 1 followed by a 3. It is with a 2 followed by a 3. And it is with a 3 followed by a 2. So here's where it gets a little bit confusing. Is that, do I count 2 and 3 and 3 and 2? And our tree diagram is telling us these are unique situations. Getting a 2 out of this box, I guess you could think of it as the blue 2, followed by a 3 out of box 2 is definitely different than getting a green 3 out of box 1, followed by a 2 out of box 2. So the probability, there's 3 favorable outcomes. So for a little Roman numeral 2, the probability is 3 out of 12. And of course, you can reduce that down to 1/4 if you wish as well. Okay, so a little Roman numeral 3, we're now being asked to determine the probability that the sum of the 2 numbers on the card is less than 7. So of course we'll just go through our sample space here. I guess I'll try to make space and get at my little Roman numeral 3 down here first before we start checking off favorable outcomes. There we go. So the sum of the 2 numbers is less than 7. So 1 plus 2 is definitely less than 7. 1 plus 3, 1 plus 4, 1 plus 5. 2 plus 2, 2 plus 3, 2 plus 4. And 2 plus 5 is 7, and that is not less than 7. So now we move on to the last, I guess, chunk of our sample space, where we got 3 and 2 and 3 and 3. And then we have 7 followed by an 8, which definitely aren't less than 7. So our probability now, if we count up our favorable outcomes, is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 12. And of course, you can reduce this as well. We'll say 9 out of 12, or you could divide by 3 top and bottom, or say 3/4. Okay, Roman numeral 4, the product of the numbers on the cards is at least 8. I guess I'll get rid of these little checks, because we're going to start fresh again. The product of the numbers is at least 8, so 8 or bigger, of course. So let's go through and say, is the product bigger than 8? No, that's 2, 3, 4, and 5. So none of those have a product bigger than 8. And then we're at 2, 6, 8. Now is it, yeah, at least 8, so we can actually count 8. Double checking my wording again here. So 8 is at least 8, and of course 10 is at least 8, and then we have 6, which is definitely smaller than 8. So 9 is 8 or bigger, and we got 12, and we got 15, which means for a little Roman numeral 4, the probability is going to be 1, 2, 3, 4, 5 favorable outcomes divided by 12. And of course, we can't reduce that, so we're down with one more. Okay, so little Roman numeral 5, where we're trying to find the probability that at least one even number is chosen. So if we look at the first part of our sample space here, and again, we'll check off our favorable outcomes. If we have a 1 followed by a 2, well, the 2 is even. 1 followed by a 3 is no even numbers, so we're looking basically for at least 1. So there's a 4, an even number. And if we start with a 2, and then it doesn't matter what we get after that, we are guaranteed to have at least one even number. And of course, 2 of those outcomes have 2 even numbers, but we just want to include as a favorable outcome at least one even number. And then in our last third of our sample space here, of course, 3 followed by a 2 and by a 4 would be at least one even number. So that gives us 1, 2, 3, 4, 5, 6, 7, 8 favorable outcomes. So our final probability here is 8/12. Of course, you can divide that by 4, top and bottom, and get an equivalent probability of 2/3. Okay, so now we'll look at exercise set 8G, which is starting to deal with the concept of independence, which is a very, very important concept in probability. And please be aware, independence and mutually exclusive events are very, very different things in probability. And I'll put a link in the description, actually, of a video I created that really contrasts the meaning of the word independence and mutually exclusive. But for now, just keep in mind they sound similar, but they are actually very different. So we have a couple of pieces of information here given. We were told the probability of the complement of E is the same as the probability of F, which is 0.6, and we know the intersection, probability of the intersection is 0.24. So before I do anything, I think I'm going to start organizing stuff here in my Venn diagram sitting here. So I'll try to get a tiny 0.24 in here, kind of sideways. So that's the probability of the overlap, and if I know the probability of my entire F circle has to be 0.6, then I just need to subtract that from 0.6 and get a 0.36. It's the probability of, I guess, the F only part of my circle, but if I add those two probabilities together in that F circle, I get the 0.6, which is the given information. And now for part A, we need actually to figure this out before we can complete our Venn diagram. So we were also told that the complement of E was 0.6. So that means all these probabilities outside of the E circle is 0.6. So that would mean that the probability of inside the E circle has to be 0.4. And I guess maybe a more formal way of doing that is to say, well, the probability of event E is 1 minus the probability that event E doesn't occur, or the complement. Of course, that's going to be 1 minus 0.6. Giving us a 0.4 is the total probability in our E circle. So that means if we got 0.24 in our overlap, we need another 0.16 in the E only section of our Venn diagram. So again, just a quick recap, the complement of E, the probability of the complement of E is 0.6, so everything outside the E circle is 0.6, which simply means everything in the E circle has to be 0.4, the remaining percent out of 100, written in decimal form. So now that we have that, we can actually finish our Venn diagram. So if I have 0.4 in my E circle, I already dealt with the 0.24, so I have an extra 0.36 in the F only section of our Venn, and if I add those probabilities together, we get 0.76, and we realize I'm actually still missing 0.24 or 24% of our sample space. So there's another probability in the outside region here, outside of both circles, that kind of confusingly is the same probability as the intersection. And knowing IB, they probably did that on purpose. It's just a coincidence that those two probabilities are the same. So now, for part B, explain how you know that these two events are independent. Well, let's see. What is the definition of independence? Well, the definition of independence is that if you want the probability of E and F, that it doesn't actually matter that it doesn't matter that E occurs. You just take that probability and multiply it by the probability of F in isolation of each other. E occurring has absolutely no effect on the probability of F occurring. So if that's the case, we could say, okay, the probability of E, which we know from part A, is 0.4, and if we just chain that together with the probability of F, complete isolation and not worrying that E has occurred, we'll say that that still is going to stick at 0.6, and if we multiply those two probabilities, we get our overlap. So this is actually evidence that we have independent events. That's simply because what we just showed here, if you have independent events, you can just multiply the two probabilities together, and you don't have to worry of the first one occurring or the first event occurring, because it will have no effect on the second event. Okay, and I guess that was what little Roman numeral 1 here. Put that in, which is a bit of a nuisance. There we go. That means we should pull down here a little bit and see if we can squeeze in the second part of part B, which is little Roman numeral 2, which is actually an easier question, because they're saying, explain how E and F are not mutually exclusive. Well, they're not mutually exclusive because the probability of the overlap is not 0. So we would say the probability of E and F is not equal to 0. Okay, so events, I guess we can write them out. What are they? E and F cannot be or are not mutually exclusive, and you can get away with abbreviating that in probability. Okay, so these events are independent, but they're not mutually exclusive, and that confuses some students because they kind of think those words are saying the same thing, but they're saying very different things. If you have events that are not mutually exclusive, there's a possibility of both events occurring. And if you can chain those two probabilities together and not worry about which that one event is affecting the other one, and if that probability works out to give you the correct one from your Venn diagram, then you also have independent events. And then finally for part C, I think I'll just stick that here since we have space, because I want to still be able to see my Venn diagram, but ideally that should go below to make it easy for your examiner to find your work. We are now trying to figure out the probability of E or probability of not F occurring. So let's see if we can get it from our Venn diagram since it's complete in front of us. So we have to be basically in the E circle, so it can be either this probability or this probability occurring, or we could have F not occurring, right, which of course would include this probability, and it also includes that 0.16 again. So we don't want to count that 0.16 twice. We just have to count any probability that occurs in either the E circle or outside of the F circle. So if we sum those three probabilities together, and of course if we add this was what, 0.4 in total. So if I add another 0.4 here, we're going to get a 0.64 as our probability. Okay, I want to have another look at letter C, and instead of using the Venn diagram to calculate our probability of E or not F occurring, which was the 0.64 we got, which remember was just including anything that was checked off in our Venn diagram there, we can actually use the rule of sum as well to calculate this probability, and that approach actually highlights another pretty important concept that IB loves to focus on as well. So if you have a union, we could set that up as the probability of E or F complement, and we can use our addition rule or our rule of sum, whatever you want to call it. All I think of is that if I have an or probability of an or, I can separate that into two individual probabilities, probability of the first plus the probability of the second event. In this case, it's a little weird being F complement, but still the individual sums, and I would expect that there's probably a probability of both of them occurring that I potentially would have double counted as well. So here's where your AND comes into effect, probability of E and F complement. Now we know all these probabilities, at least the first two are pretty obvious. The probability of E is the sum of those two probabilities inside the E circle, remember from before, Or we could go 1 minus the 0.6. Since the E complement was 0.6, 1 minus 0.6 gives us 0.4. And similarly, the complement of f, if the probability of f was 0.6, then the probability of the complement of f is also 1 minus 0.6, or 0.4. And here comes, I guess, the important point that I wanted to make, which is why we're duplicating a solution here with a second approach, is that if we have an and statement and we know that events E and F are independent based on our work previously, then events E and the complement of F are also independent, which means we can chain these two probabilities together in isolation of each other. And that would mean that E is going to have no effect on F. It's also going to have no effect on F not occurring, since there's no interplay, I guess, between those two events whatsoever. Which means now we can take these two probabilities of 0.4, and after we add them together, we have to multiply them here to get the overlap or the intersection of these two events. So 0.4 times 0.4, I guess I can write it out. Of course, that's going to be 0.16. So we'll have a pair of 0.4s added to get 0.8. We'll subtract away 0.16. And if we do that a bit of arithmetic, we get a 0.64 as the probability of E or not F occurring, which of course was the same as what we got earlier. It's relying on our Venn diagram. But please kind of hone in on this portion of that calculation here, is that if E and F are independent, well, so is event E and F complement. And if those are independent, you can separate them into two individual probabilities and chain them together with multiplication to get the probability of that intersection. And you can do, I guess, this calculation in two different ways, whichever you prefer. Okay, so let's summarize this idea of independence. And remember, if events A and B are independent, well, you can actually calculate the probability of A and B occurring by multiplying the two individual probabilities together in isolation of each other. And that's because event A will have no effect on event B, and event B likewise will have no effect on event A, and you don't have to worry about any interplay between the two events if they are independent. And the sneaky part of independence is that if events A and B are independent, well, then you can introduce some complements into the mix as well. So if A and B are independent events, well, so are A complement and B, A and B complement, and finally A complement and B complement. So this would allow you to calculate three other intersections. You can calculate the probability of A complement and B occurring the same way you calculated probability of A and B occurring, a product of the two probabilities in isolation, and the same with A, probability of A and B complement, and the probability of A complement and B complement. So just keep that in mind, that quite often IB will tell you that events A and B are independent and then give you one of these sneakier probabilities to calculate. Okay, the last problem, we'll look at number 9 from exercise set 8G, where we will, I guess, put into practice what we just looked at regarding independent events. So A and B are independent events, and we know the probability of A and the probability of B, so we can go ahead and calculate the intersection, or the probability of the intersection, simply by chaining those two probabilities together. And keep in mind, you can only do this when you have independent events, because A is not going to alter B in any way after when it occurs. So we'll have 0.9 times 0.3, which is 0.27. Okay, now on to letter B. We can calculate this probability in the same way because it's another intersection. And if A and B are independent, well, so are A and the complement of B. So this will be the probability of A again, multiplied by the probability of B complement. So of course, if the probability of B is 0.3, then the probability of the complement of B will be 1 minus 0.3, or 0.7. And A, of course, hasn't changed. That's still 0.9. So the probability of this intersection is going to be 0.63. Okay, and our last question here, I'll get a little bit more space and we'll look at this union. That's a little bit, I guess, more time consuming than these two intersections that we calculated. But of course, anytime we have a union, we can set up our rule of sum. So this is going to be the probability of A union B complement, or A or B complement. Of course, we split it up into two individual probabilities and add them together. And we already know both of those probabilities, but of course we'd have to take some care to make sure we're not counting the probability of the overlap more than once. You can see it's coming full circle now because we actually have the probability of the intersection of these two events. So probability of A is 0.9. Probability of B complement is 0.7, which we dealt with in letter B. And of course now we get to subtract away that 0.63. So we'll have 0.9, and I guess if we look at this, will be the difference in those two percentages, or I guess decimals, is 0.07. So this will be 0.97. So almost 100%, but not quite, is the probability of this union of A or not B. Okay, and just to demonstrate that what we did in our, I guess, formulaic calculations there is legit and correct, well, I think rely on a more basic approach and quickly redo these three probabilities where we basically just rely on our Venn diagram. So we would still calculate the intersection of A and B the same way because these are independent events, and we could pencil in 0.27 right away. And then the rest of this stuff we'll just pretend, I guess, that I'm not going to use. Pretend it's not there. There we go. So how would I fill in the rest of my Venn? Well, I know the probability of B is 0.03, so I can fill in the B only part. I need another 0.03. So if I add those two decimals together, I will get exactly 0.3, which I want. And then in the A only section of the Venn, I would have to take that 0.27 away from 0.9, and of course I would get here a decimal 63. And that should sound familiar because, of course, we calculated that using the formula and the fact that A and B are independent events in order to get that 0.63. So what's missing in our Venn here now is, I guess, that outside number. If we have a 0.9 and another 0.03, then, of course, this is going to be 0.07 remains. So I can add up those four probabilities and get 1 or 100%. And now I guess we could just quickly go through and calculate letter B because we have the answer sitting in our Venn. The probability of A, but not B, of course, will restrict us to this section of our Venn, so-called A only section of our Venn diagram. So that probability, and I guess we could quickly write it out, probability of A and not B, staying in the A circle but avoiding the intersection, of course, is 0.63. And your work and your evidence could simply be the Venn displayed off to the right here. And then part C, if we want to figure out A or not B, I guess we'll do our check mark approach. So we would go through and say, okay, I could take anything that's in my A circle, so those two numbers, and I could also take anything that's not in B. So I can take that number, and I can include this number, and the only thing, of course, we are not using, I'm sure you can see, is we're not using this section of our Venn, the so-called B-only section, so we're going to use this 0.9. We're going to use this 0.9 and that 0.07, so of course this probability is going to be 0.9 plus 0.07, which is 0.97. And I guess I'll put my label on here one last time. So this shows you that you don't have to rely on your formulas to do these two calculations. Your Venn is still useful, but I think more to the point, it's also showing us that if we have independent events, then when we introduce a complement, we still maintain our independence.